Alright, so in this video, we're going to be going over the CubeSat standards as of 2014, I think is the current revision we're looking at. Mostly because, at least I know for a lot of new people, if you're anything like myself, some of the requirements will make sense, other ones will seem like gibberish, and sometimes you're not sure. Some of the requirements will look like a crossbreed of both. So I have Greg here, who knows a little bit more about this stuff than I do.
Hi.
So yeah, I guess we'll read through them. Stuff makes sense to me. I'm gonna more or less assume it makes sense to you, and if something seems like gibberish, Greg will explain everything to me because he knows it all. And yeah,
Almost.
Wikipedia.
Pretty close.
Wikipedia refers to him a lot.
Yes.
So yeah, we'll start off at the top. CubeSat Specification 3.1. CubeSats which incorporate any deviation from CDS will submit a DAR and adhere to the waiver process. I have no idea what that means.
So I think
CDS
is this document.
I think they have a
CubeSat Design Specifications.
They do have design specification shall submit a deviation waiver approval process.
Yeah, so for that we'd if we have to do something, if we can't follow one of these rules or one of their specifications they give, we will basically fill out a form and send it to our launch provider and say we can't meet this. Here's what we'd like to do instead. Does that work for you? And then we'll go back and forth, and they'll say, all right, we either you gotta absolutely do this one, or we can waive it if you do these other things.
Seems pretty sure. Gotcha. Okay. Next one. All parts shall remain in the CubeSat during launch, ejection, and operation. No additional stasis debris will be created. Seems pretty straightforward. Any comment?
Hold together.
Okay.
Maybe consider. I don't think that includes propulsion device.
I was wondering.
But we'd have to talk to them.
And actually, that I wonder about what the So the next one is no pyrotechnics shall be permitted. That strikes me as saying that propulsion.
I think pyrotechnics are different than propulsion, but you should talk with the launch provider specifically when it comes to propulsion stuff, because the CubeSat design specifications are only a basic thing. If the launch provider says "fuck that, we're not doing any of this," then
I like it.
It doesn't matter.
I like it, but truly, I think it's pyrotechnics are just those explosive or things.
So there are things like explosive bolts that you can use to separate things, and there are I think explosive rupture valves that you use to open a valve, basically.
Okay.
Okay.
And then any propulsion systems shall be designed, integrated, and tested with accordance to that document.
Yeah, so you're going to have to Google that and figure out what it is.
Yeah, so we're not going to go through that document. Propulsion systems shall have at least 3 inhibits to activation.
3 different valves that are controlled by 3 different things, something like that.
Okay. Gotcha. So you have your whole, maybe your brains at the computer checking
so you have to on your computer you have to hit 3 different buttons
or you have 3 different buttons to inhibit it, or
so you're not going to just type in one command and hit enter and it's going to work. You need to do manually do 3 different things to make it work. This
one I have a question about. Total stored chemical energy will not exceed 100 watt hours.
Okay. Not entirely sure. That could be battery power. That could be chemical reaction sort of stuff. We're honestly not sure. I think we're going to be okay either way.
Yeah.
Or we can calculate how many joules that is and try to figure it out. But
gotcha. But okay, that would probably be
just an energy amount. Yeah.
Okay. Higher capacities may be permitted, but could potentially limit launch opportunities. Hazardous materials shall be according to this document.
Yeah, so I think we can probably look at that document to figure out what is hazardous. I don't think anything we have is hazardous. But we should when we give our list of all the materials, they should be able to look at it and say this is hazardous.
Yeah, actually, I think I remember looking at that document, I think a couple weeks ago, and a lot of it was just referring to other documents.
Yeah.
The only thing I got useful out of it was your CubeSat shall not contain it will be considered useless, or it'll be considered space junk or hazardous if it's not doing anything useful. That was the definition.
That's weird.
Yeah. Next one. Yeah. CubeSat material shall satisfy the following low outgassing criteria and prevent contamination of other spacecraft during integration, testing, and launch. You can find it. The materials can be found there. For those of you people who are not familiar with outgassing or total mass loss or collected volatile condensable material, what the hell do those words mean?
So you got regular gases and vapors and whatnot. The issue is that if you some of them like to seep into materials, especially plastics and adhesives, and just at ambient pressure because they've got a little bit of a positive pressure just being around them.
Mm-hmm.
And the problem is that once you get into space, you're now 1 atmosphere lower pressure, and they start to come out of that material.
Gotcha.
And the real concern is that some of those are going to then either create just a cloud of mist that can damage solar panels, or it'll recondense onto other stuff. Usually solar panels. Then solar panels don't work as good, and they especially like to condense on optics and anything that's like cooled. So a lot of like really high tech camera systems or optics are cryogenically cooled, so they're very cold, and so stuff condenses back on.
So you're like, there goes my pristine picture.
Yeah, so that's why we want to be careful with outgassing. So things like metals generally don't outgas.
Mm-hmm.
Technically, everything outgasses just a little bit. No matter if it's a metal, if it's solid, no matter how cold it is, whatever. But realistically, there's only a few you got to worry about. I think cadmium was especially bad. It's also like super toxic, so we don't want to deal with it. And then I think it was either zinc or I think it was zinc, one of those metals.
Like magnesium or...
Magnesium. Let's Google it fast.
Okay. But yeah, between, I think you said cesium, and then zinc.
Zinc is bad. Magnesium is also bad, apparently.
Oh, okay. So materials for use in... Oh, that's good. So for people who want to Google, like, general materials to not use in a vacuum, which is space, mind-blowing, search on Wikipedia, materials for use in vacuum, and they have a nice list about materials to avoid, which include everything from what he stated to PVC and different types of plastics.
Oh, there's a ton of stuff here.
Yeah, so knock yourself out. I was not even aware of that, but that is
that's a definitely good source to have. It's not an in-source.
Yeah.
So you do need to go back and say, is the total mass loss less than this one?
Yeah, but that's a good place to start, and then you can verify that. Cool. I did not even know that.
Cadmium and zinc are especially bad on fasteners. So a lot of fasteners have zinc coating.
Oh, jeez.
So that's why I'm getting all the black oxide, because that's the only other option on McMaster. So.
Gotcha. Yeah. I learned. We might have a whole section just dedicated to that, because that was really good.
I mean, like, if you have wires, you got to make sure the insulation on those wires doesn't outgas, because it might. And this could either be a material turning to a vapor, or it could be like water got trapped in it while it was in an atmosphere, and then it comes back out again when it's up in space.
Gotcha.
It could be stuff like that.
Cool. That is all good to know. So refer to those resources for these specific requirements.
Yeah.
The next few requirements, looking at them, look like just selfless plugs.
So for total mass loss, that's literally just you weigh it, and then you pull a vacuum on it, and then you see how much mass did it drop.
Okay.
It seems like a pretty dang easy thing to meet, but
and the collectible.
I guess it's better to point out that that needs to be done for each separate material. And then the overall percentage is going to be less. So they're not actually going to test that on our CubeSat. We just need to show that all of these materials we're using have been tested.
Gotcha.
And then collected condensable volatile is all that stuff that vaporized off. If it then passes over a cold plate, will it recondense on that? So
gotcha. So you have in your vacuum you have your thing on a scale. Pull the vacuum on it.
You have your material on the scale.
Yeah. And then you have like a cold plate in the vacuum as well, and then you can, if you want to, calculate it by hand.
Yeah, I don't know exactly how they do it, but it's roughly like that.
Okay, that's good to know. Cool. I think that pretty much covers those two parts. These two requirements look like selfless plugs.
Yep.
Magnetic field strength, that's actually relevant to this launch because we're using a magnet torquer.
Yeah.
So
I think we're okay because we're not using any permanent magnets. So we're just our magnet torquers won't be charged up when we launch.
So this is like inside the launch field.
Yes, I believe this is launch field because it says that they can interfere with the P-pod. It might include other things, but we'll just have to talk with the
talk to your
control
talk to your launch provider if you have questions.
Yeah, seriously.
The CubeSat shall be. Whoa! I didn't even know this was.
Yes.
What does this mean?
Yes. So basically, when we're in the fairing somewhere, and as the rocket is lifting us up, the pressure outside is going to be dropping. Mm-hmm. And we want to make sure that the gas that stays in our CubeSat, like right now there's a ton of gas inside of our CubeSat because it's all empty. That needs to escape out safely.
Okay.
So they designed the P-pod so that they can vent that gas. But they also need to make sure the CubeSat is not all sealed up.
Gotcha. Do you know, well, I mean, we have pretty big gaping holes in here, so it seems like it won't be a problem, but do we really need to test that?
It's literally just a math problem. So, a ventable volume, so how much volume is in it, divided by what area it could escape at. So we'll just take this area and just the whole volume and say, is that less than 2,000, which it is. But,
okay.
You know, like it's really easy to meet that. We just need to show that we did the calculations.
Gotcha.
So
cool. Okay, mechanical requirements. So for this video, we're just going to go over mechanical requirements since that's all we can speak to, and we're also not electrical engineers. So we're going to talk to that. So CubeSat Pico shapes. Yeah, okay, so this is the coordinate system for it. We're not using actually that coordinate system for our CubeSat. That's just, I guess, for your general reference if you need it in the future. The CubeSat shall use the coordinate system for appropriate size. Appendix B, if you scroll all the way to the bottom.
And note that there are different P-pod launchers, or different CubeSat launchers, and so they may change it. I doubt it, but they might, so just keep that in mind.
So refer to your document and your launch service provider document. You need a different coordinate system. Configuration shall be appropriate for the section in Appendix B. Again, if you scroll to the bottom, Appendix B, it's just like a big, here's your coordinate system, here's what your dimensions look like, here's what can extend out, here's what can't. Next start. Most of this extra volume is shown in Figure 6.
So if you're doing a 3U, you might as well take up that extra volume because almost all of them are going to have it.
Yeah.
So if you're having, say, a propulsion system, you can shove part of it in there. It's great. So, but if you're doing like a 1 or 2U, you can't be guaranteed. It'll limit your launch opportunities by trying to include that because only one of the 3 1Us can use it.
Yeah, and actually, you know what? I'm going to scroll to Appendix B just to have whoa, Jesus, this is fun.
Oh boy.
Big. Right, I think that's Appendix. Which one? Section 1, that's the one you...
farther down. Yes, it's going to show the different... Oh, yeah.
Appendix C.
That's
here we go. So, this is the extra space for the 3U. If you have a 1 or 2U, don't expect to have that space.
Yeah. There's like a slight chance, but don't rely on it.
Yeah, and also if you need to reverse engineer a P-pod, this is where you can do it. Hopefully you don't have to do that. But you might.
You can try it.
Yeah. Actually, I guess Sean, that's what he made his rocket from. He literally just reverse and made it. And I wish we had it because that was like the perfect P-pod. But anyways, that's a time-relevant complaint.
Right, back up to the structural section thing.
Yeah, right here. The Z negative face will be inserted first into the P-pod.
Great, we don't care.
Just make sure you're referring to... Actually, do we know... So the Z negative face, is that relative to their Appendix B document? I think.
Yeah, it's in their appendix.
Yeah, so you use the coordinate system.
Should be the same.
So if you go to the Appendix B, should we know it? We'll do it again, just so it's very clear to people, because I know sometimes I make the mistake. So your negative Z, this is what your P-pod looks like.
I think that's this side.
Yeah, I don't think they can see it on camera, but yeah.
It's going to be this side where the payload is on.
Yeah.
I think that's right.
Yeah, that seems about right. So negative Z.
Or it could be this one, you never know.
Yeah, who knows?
But we don't actually care as long as we put those.
For those of you who can't see our CubeSat, we are holding it in our hands. It's beautiful. Anyways, plus Z, negative Z, that side's going in first. You've been warned. Next one. Note the components. Okay, yeah, just refer to that picture that I keep scrolling down to for most of these requirements. No composite degree shall exceed 6.5 millimeters. Normal to the surface, completing accepted checklist. Protrusions will be removed from the plane of the rails. So that is
good to know. And it also technically doesn't say. I mentioned a while ago, but this space just right here doesn't technically give it that to us. So
yeah.
I don't want to talk to him about that.
Yeah. Oh, yeah. I'll talk to you more about the launch service provider stuff because I emailed them and yeah.
Okay.
Where were we? Checked it. Yeah, measurements for the rails. Deployment rails shall be constrained by the CubeSat, not the P-pod. Pretty straightforward. Rails shall have a minimum width of 8.5 millimeters. Pretty straightforward. Surface roughness less than 1.6 micrometers. If you want to measure that, you could probably get like a micrometer if you really wanted to. But
you need a special surface roughness tool for that.
Okay. So
it's the shop here doesn't have it. So honestly, I think we're just gonna have to just like smooth it really nicely and just pray that it's good.
Gotcha.
I mean, Kurt's shop might have one, but we'll see.
We'll ask around. Hopefully, you guys in the future who are making CubeSats, maybe that part's been sorted out.
Hopefully we'll have a tool.
Who knows? The edges of the rails shall be rounded to a radius of at least 1 millimeter. Pretty straightforward. The ends of the rails of the plus Z shall have a minimum surface area of 6.65. Yep. I found out that the hard way because I didn't realize the rails had a minimum width of 8.5 when I made my model.
The main width versus
the surface.
Very tippy top.
Yeah. So be sure to note that because I didn't, and luckily the people who were judging me didn't notice that part. At least 75% of the rail will be in contact with the P-pod rails.
So they don't technically specify where the actual rails are going to be. Like, are the rails going to cover the entire thing, or just like a part of it, which would make it a little hard since we don't have the design. But I think we just assume because
it looks like the rails just like kind of fit in the void area. For those who can't see the picture, we're looking at like an edge of a CubeSat right now, and if you look at the P-pod, it looks like there's some rails it sits on. So we're just assuming it's like these two flat faces. Actually, I'll see if I can pull.
Yeah, so we should be okay because they're not trying to screw us over.
So if we're looking, like this is like our CubeSat, we're looking at like this edge here, and we're assuming like, okay, there's about 8 of these edges because you have 1, 2. So we're assuming those 8 edges, if you took the area of those, 75% of that area must be in contact with the P-pod rail. Where were we? God, there's... still down, I
think there,
25%, maybe recessed with no... See. Maximum mass, 1.3. Okay, these are all for the different... Use this is your mass. If you have I didn't realize that you could get more mass depending on if you talk to your launch service provider.
And we actually might, just because we're not actually launching in a P-pod. So Kenneth mentioned that we might
be able to use more mass, but
which we don't need any more mass.
We're
probably gonna have like maybe half the mass be used anyways. So. But it's good to have that. Anyways.
I never realized that. We don't. Most of these requests may never apply to us. Well, go through them anyway, follow them, and then if you luck out like us...
You gotta follow them and just overdo it if we have to, but
Center of gravity shall be located within 2 centimeters from its geometric center in the X and Y direction. So you could, I guess, hand calculate...
You'd have to do that in probably just SolidWorks.
Yeah, actually, I think the senior design team said we could do that in SolidWorks.
But we do need to make sure all of the parts we're using are decently correct.
Yes.
Like each of them has a proper center mass to their dimensions.
So measure...
So keep that in mind.
At least for the center of mass, you can measure the weight perfectly fine, but for center of mass, how do you determine that?
Not easily manually. I think just calculation is the way we're going to go. If you really wanted to, you would... let's see, you can put it on a... You can very carefully suspend it and draw a line down it. That line has to go through the center of mass, basically. And then you do that from another point.
Okay.
And then
you can just roughly
approximate. It's not great, so we're going to want to rely on the SolidWorks.
Between SolidWorks, if you really want to do that, you can verify that. Let's see. These are all different.
Other sized.
And you have to use these materials.
The main CubeSat structure on the rails.
6061 is much cheaper, so use it. Actually, I don't. I've actually
7075 is slightly stronger, but it's also harder to machine, and we don't really care. We're already underweight to begin with.
If you decide to be experimental and use other materials, you should submit a waiver.
Great. Just reiterated the first point we read already.
Exactly. Pretty much all of these. If you want to change anything, talk to your launch service provider. Launch service provider will contact the P-pod. The standoff shall be hard anodized aluminum to prevent any cold welding. So is that because I think for anodized aluminum, You can buy, I think, anodized aluminum from McMaster-Carr. So would that be hard anodized, or is that?
Probably, yeah.
Okay.
I didn't know.
While he's looking at that, I'm just going to go over some of the other requirements. We'll come back to 30.216. When 1, 1.5, and 2, you shall use separation springs. You can get these ones down here. Contact your local CubeSat at CubeSat separation spring provider. Yeah. Hard so the anodized, does that look hard anodized?
It appears to be.
Okay.
It's black. The black stuff tends to be hard anodized.
Okay, so if
you can get other colors like blues and reds, which are really pretty, but they're not hard anodized. So.
Mm-hmm. So if you find, if you're on McMaster-Carr, wherever you're ordering your aluminum, and you get anodized, like if you get the black stuff, probably good.
Just make sure it's also the material is tempered properly.
How do you know? So tempered.
T6.
T6.
So I think these are all okay. So T6 and T6.
So
whatever.
Yeah.
I think these are all okay.
Is that the same for the aluminum 775? You get T6 tempered.
I don't know. I'd have to check.
Okay.
Yeah, there's a little weird though.
Okay.
They have a very low yield strength. So I need to check. We need to check that.
Okay.
But we can. It's also really cheap to get it anodized, so
yeah.
Might as well just
okay. Anyways, hard anodized. Already kind of went over the separation springs. Not required for 3 CubeSats because you take up the whole container.
Because you don't have to separate from any CubeSat.
Yeah, because you are the boss and the bomb. Let's see. Recommended compressed springs shall be at or below the level. Yep. Okay. The level of the standoff. The standoff is just the. What is that? Is that just the part that, like, if you have the edge of the rails, the little flat part here that's 6.5 millimeters, the little threaded part here is like touching that? It's for the compressed.
Yes. So it just needs to stick out 0.16 inches past that is all.
Because that's how long this part is.
That's how long this plunger is.
Oh, the plunger. So it needs to stick out.
The plunger needs to stick out by that much. The rest of it will all be inside of the foot, basically.
Because that's right. Because it's getting threaded inside of here.
Yeah.
I think we
so
still need
threaded in, so that end's pointing out.
That makes sense. We still need to put those threads in.
Yeah.
Oh well. We'll get that later.
I was thinking we'd do that after we put in the separation spring.
Yeah.
Or not
the switch.
Switch.
Yeah.
Just because this we can put on any corner.
Yeah.
Separation switch might actually matter. So.
Excellent. And yeah, so that's. And
we already bought that custom piece, so we're good.
Electrical, we're not electrical, haha. Operational requirements, that's just all like communication stuff. Yeah. Testing requirements. Usually, you'll be given testing requirements by your launch service provider. But if you don't have requirements from your launch service provider, like we did, because, I don't know.
If you don't have them yet.
Yeah. If you don't have them yet, use the GEV standard. The GF... What is that? This thing.
GSFC STD 7000.
Yeah. So there will be all these tests here. This document will have the specifications you can do all these tests to, minus the visual inspection. I don't know if there's anything.
I don't know.
Yeah. But anyways, they will have numbers you can plug in for random vibration, thermal back out, and shock testing. Refer to this document. That's a pretty conservative one from what I remember.
Yeah. So it's generally conservative. However, the launch provider will trump that if they decide that that's not good enough.
Yeah.
So I wouldn't suggest actually testing at GEVs. You should wait until you get the official ones.
Yeah, but if you need to do like SolidWorks model simulations or stuff like that, GEVs should be okay. Hopefully, because at least future CubeSats will have documentation from us, you can use our documentation and our test levels, previous ones, for testing whether your structure is good. So random vibration, just take your CubeSat, excite at a bunch of different random frequencies at different levels. Thermal vacuum bakeout, that's to check the outgassing. I didn't realize. I was checking outgassing, so you don't. It's not like a temperature check to see how much your thing. That's to see if you lose any mass. I didn't realize that.
Yeah, so I'm not sure if they'll actually be measuring if we lose mass. I think they'll be measuring condensation.
Okay, so you don't even. I didn't realize you actually didn't go to 60 because that. Oh, so this is not like a will your thing survive hot and cold? It's
well,
just
it
like,
also is that. But
okay, Well, slightly that, but it's mostly just to see.
Yeah, so part of it is you can get rid of some of that outgassing, the stuff that would outgas, by doing a bake out.
Mm-hmm.
And so after that point, I'm pretty sure they're going to do this testing for us.
Yeah.
After that point, then they'll just keep it in a sealed container to make sure it doesn't, nothing recondenses on it.
That makes sense.
So that way when it goes up into space, it doesn't have as much, even if that already would have been less than the
Gotcha.
7.
That makes sense.
They're just trying to further limit it a little bit.
Yeah. So shock testing, you're taking your CubeSat and you're like putting, I think it's like a little impulse.
Dropping it or something.
Yeah, just really high G impulses into your CubeSat and make sure you survive.
For large spacecraft, they also do acoustic shock, which is just sound waves. But that's pretty interesting, but we don't need to worry about that because we're tiny.
One day, kids. Hopefully one of you.
Someday.
But now it's visual inspection. They look at it. Yeah.
Make sure the measures are good,
Yeah.
Make sure it fits in the space they gave us.
Yeah. This is like a stuff that I didn't even learn about, so this would be good.
Qualification.
Testing philosophy. Qualification versus proto-flight versus acceptance.
Yeah, so the hardest of those is qualification.
Yeah.
So qualification is, you would do qualification testing if you made 2 identical models.
Mm-hmm.
You put one of them through qualification testing, and if it does not fail doing that, then the other spacecraft, that one doesn't have to be tested as hard.
Yeah.
So you can use that if you really only want to test one good spacecraft once, as opposed to twice, where you'd go through the let's see what else.
Yeah. Actually, maybe just give like a little more overhead.
Yeah. So you have either you have 2 CubeSats, you want to put both of them up, and by doing qualification testing on one of them, then the other one doesn't have to go through as much. Or you have one that flies, one that doesn't fly, but you make them exactly the same. And the one that doesn't fly, then that one you shake the hell out of and make sure it doesn't break.
So like,
and then the other one you can not have to go through as high a qualifications.
Yeah. So it's like an overview. So these are like 3 different like intensities you're testing. So you run all the same tests, but qualification testing gives you a more intense set of numbers.
Yes.
Versus like acceptance gives you like, oh, okay, this is like a lower set of numbers, so you don't end up breaking, like, because the more intense set of numbers you could, even if your CubeSat survives, okay, great, it survives that, but then on the actual launch, because it's been like tested so hard, it may not survive that launch because of like fatigue. Stuff like that.
So that's a good case of more testing is not always better.
Yeah, so that's why
if you do the qualification, then it might have damaged it some.
Yeah.
It may get to the point where it kind of starts to damage it, but not quite enough to be noticed.
Mm-hmm.
And I mean, this whole vibration testing stuff is just how, like, none of this stuff is super accurate. So they have to have these extra layers of stuff.
So if you have, like Greg was saying, if you have 2 CubeSats, you can test one of them, which is like your test dummy, just doing all your testing at qualification levels at the higher, really intense ones. And if that CubeSat makes it through that, you can test your actual CubeSat at the acceptance level.
Yeah, only at acceptance level, which is basically equivalent to what the actual launch would be.
Yeah, but if you only have one CubeSat and you want to test it because you don't have any others and you're broke,
you don't have any other exact models.
Yeah, you test it at proto-flight, which is slightly above acceptance, so it does it there, but it doesn't go all the way up to qualification because you don't have 2 of them.
But then you have to test it one more time at acceptance also.
So you
have to do at least 2 no matter what. It's just maybe not on the same one.
So you do like a proto-flight beforehand and then acceptance.
So we'll be doing the proto-flight, and that's what we'll go with to NASA or whatever, and then they'll do the acceptance one right before.
Gotcha. Okay.
But we should be there at the time. So.
Yeah, here's your whole flowchart. I didn't realize they had a flowchart.
So that's they'll do.
And they'll do it in the vibration shock testing.
Yeah.
Oh, because this is where they do it in the P-pop flight system, I think.
Yeah.
Yeah, and then flight. Yeah, the acceptance. And talk to these people because they're really nice, and maybe some of them are still at their positions. I know he is.
He'll probably get ignored. But
this guy, Jordy, responds to my emails. I don't know if he'll still be here, and he hasn't been responding to them recently.
Yeah,
so,
I have the feeling he's not really the.
No,
he's not he didn't put his name on here as like the question answer.
No, he was one of the guys who
more as
developed the program, but
more as a like if you have really high level questions. As opposed to just
but
basic questions.
for all the questions, what do we say,
hey.
kids?
Give it a try.
Gotta contact your launch service provider. So there you go. That's a little, I guess, overview of the Peapod, just the CubeSat qualification document in regards to structures. If you follow that, even you should be pretty good for like any launch service provider using like the CubeSat form factor. That's all you really need to know. Go make it.